Read.
Assalamualaikum, ma'am.
Alaikum salam. Okay, how many students are here? Okay, so it's 2:59, and we will start at 3. Let me share the screen.
Okay, ma'am.
Okay, share screen. Okay. So let's wait for 1 more minute, and then we'll start. Okay, it's 3 o'clock, but there's so few students. Do you all know that we have final exams in January? Yes, ma'am.
Yes,
So
ma'am, we do.
so we only have like a month left to study, and we have 3 chapters, so we have to hurry up a bit. We'll start by this presentation. Energy levels and spectra. This is where we left off last time. So last time what we were discussing was that we said that जो electron के circumference जो circumference of the atom होता है, ठीक है? Circumference of this is the electron path, ठीक है? This circle over here, and the de Broglie electron wave has a certain wavelength associated with that. We said that it's a de Broglie wavelength. So the de Broglie wavelengths, we said that the condition for orbital stability is that an integer number of de Broglie wavelengths is equal to the circumference of the atom, right? Circumference of the electron orbit. So that is what we said last time, and then we went on. I hope that was clear. Okay, we did an example, so I hope that we can finish this chapter today, and I hope that we can also start nuclear structure chapter either today or hopefully today we'll be able to start it. ठीक है? So ये हमने एक condition for orbital stability कहा था, ठीक है? और फिर हमने यहाँ कहा था कि Rn, which is the Rn, which is what is Rn over here? Is the radius of the orbit, right? Electron orbit is equals to n square a naught, where n square is what? N is the quantum number and a naught is a Bohr radius. ठीक है, तो हमने वहां तक कर लिया था, तो हम यहाँ पे हैं अब. Now energy levels and spectra. Now some of this part will be repetition from what we have done in astronomy, astrophysics, but whatever it is, we'll finish it today, and we hopefully finish lasers as well today. Okay, so we're talking about energy levels and spectra, and we all know that various permitted orbits involve different electron energies. The electron energy En, अभी हमने calculate किया था electron energy. Are you all following? हमने अभी यहाँ पे one of the equations above हमने electron की energy calculate की थी. Where did that go? Here we go. Total energy of hydrogen atom of the electron in the hydrogen atom is given by this, ठीक है? And its negative value. So here we are. This is the total energy in terms of the radius of the orbit. Substituting for Rn from equation for 1.4.13, Rn की ये है equation, ठीक है? Radius of the electron orbit. So when we put that in this equation, we will get En is equals to E1 over N, where E1 is the radius of the innermost orbit, where N is equals to 1. Okay, so these numbers over here, these constants over here make E1. So E1 is, if you plug in the values of the constants, for M is the mass of the electron, E is the charge of an electron, this epsilon naught is the permittivity of free space, and H here is the Planck's constant, you will get here E1, minus E1, to get E1. So E1 is minus, you will get the values of these is equals to this thing, minus 13.6 electron volts. Okay, so every energy level can be represented by this for the hydrogen atom. Okay, and we've already studied this before. Okay, these levels are all negative, which signifies the electron does not have enough. I think we already did this slide before, which means that the electrons are the energies are negative, which means that electron does not have enough energy to escape from the nucleus. Okay? If the energy was positive, that means the electron would not be bound to the atom at all. Okay? So now the lowest energy level, is this recording? Yes, it is. Okay, so the lowest energy level is called the ground state of the atom. Okay? Higher energy levels E2, E3, E4, and etc., where n is equals to 1 represents the ground state, n is equals to 2, 3, 4, etc. are the excited states, are the higher states, or known as the excited states. So the first excited state corresponds to n is equals to 2. So as the quantum number n increases, the corresponding energy En approaches closer to 0. En, why does En approach closer to 0? Because all of the other ones are negative, right? The other energies are negative. So as we approach, n is going to infinity. As n increases, like n is going to infinity, what is going to happen to this value? It will go closer and closer. Its magnitude is going to be smaller and smaller until it eventually goes to 0. Okay? So that means at the state where energy is 0, that means the electron is no longer bound to the nucleus to form an atom. Okay? It won't be an atom anymore because, the electron will not be bound to the nucleus anymore. So a positive energy for a nucleus electron combination means that the electron is free. A positive energy, yeah, that means that there's no electron is not bound to the atom. Okay? Then such a combination does not constitute an atom, of course. Of course, because an atom means that electron is bound to the nucleus, to the atom, is bound in orbits around the nucleus. But we don't get that when the energy is positive. Okay, so now let's talk about ionization energy, and we know that what do you mean by ionization? Ionization is when you either remove or add an electron to the atom. And when you either remove or add an electron, if you remove an electron, then it will become positively charged. If you add an electron, then what's going to happen to the ionization? What will happen to the atom? If you add an electron, it will be negatively charged. So the resultant atoms are ionized. And in order to calculate the work needed to remove an electron from an atom in its ground state is called the ionization energy. Basically, ionization energy is the energy required to ionize an atom. So for the ionization energy is equal to minus E1. The energy must be provided to raise an electron. So basically what we said over here, that this E1 that we just calculated, it's the energy required, energy of an electron, of one electron in orbit around the hydrogen atom. Okay? So basically, if you want to create a hydrogen ion with one of its electron removed, you need to put in an energy of positive 13.6 electron volts to make it an ion with positive charge, with positive 1 charge. Is that making sense? The energy must be provided to raise an electron from its ground state to an energy of E is equals to 0. So basically what we're saying here is that E1 here is the minus 13.6 electron volts. That is the energy of the one electron, the electron in the orbit number, quantum number, orbit number 1, which corresponds to quantum number n is equals to 1 in the ground state. Okay? So this when you want to figure out what is the ionization energy, it's going to be positive 13.6 electron volts, because this is the amount of energy you need to put in to remove this electron from its orbit, because the electron in this orbit contains an energy of minus 13.6 electron volts. Okay? In the case of hydrogen, the ionization energy is 13.6 electron volts, since the ground state of the energy of the hydrogen atom is minus 13.6 electron volts. Okay, makes sense? So now we will do an example here. Electron collides with the hydrogen atom in its ground state and excites it to a state of n is equals to 3. Electron collides with the hydrogen atom in its ground state and excites it to a state of n is equals to 3. How much energy was given to the hydrogen atom in the inelastic collision? So from figure 4.15, where's figure 4.15? I don't think I included the figure in here, but the energy change of a hydrogen atom that goes from an initial state of quantum number n to a final state of quantum number nf is this. ये हमें पता है ना? Delta E is equals to, ये formula हमें पता है ना? EF is equals to E1 divided by NF squared, and EI is equals to E1 divided by N, E1 divided by NI initial squared. Are all of you familiar with this formula? This is the energy change of a hydrogen atom that goes from an initial state of quantum number Ni to a final state of quantum number Nf. Because we just said that energy is according to this formula, right? So E Ni initial is going to be equal to E1 divided by N initial squared, and E final is going to be equal to EI divided by N final squared. So we can just take the difference of those two and we will get this equation. So then we will get is equals to E1. We can take E1 common, and then we will get 1 over NF squared and final squared minus 1 over N initial squared. ठीक है? So N initial here is 1 because they're talking about an electron collides with a hydrogen atom in its ground state, excites it to state N is equals to 3. So N final is 3 and N initial is 1. So we will, and we know that E1 is minus 13.6. So we will put that in this equation. We'll get 12.1 electron volts. So basically, how much energy was given to the hydrogen atom in this inelastic collision? That is equals to 12.1 electron volts. That was the amount you needed to excite the electron. Excites it to a state of N is equals to excite the electron from the ground state to the state N is equals to 3. This is the amount of energy you need to put in. ठीक है? So we'll do another example now. Any questions so far? No questions? Okay, then. Hydrogen atom in states of high quantum number. This is another example here. That what are they saying in this example here? Hydrogen atoms in states of high quantum number have been created in the laboratory and observed in space. They're called Rydberg atoms. Find the quantum number of the Bohr orbit in a hydrogen atom whose radius is this. So we know that radius is equals to 0.0100 millimeters. Millimeters is 10 power minus 3. And this is 10 power minus 2, so it will be 1.00 to 10 raised to power minus 5 meters. And then over here, what we had the formula that R is equals to N squared times A0. So N will be equal to square root Rn divided by A0. We know what the Bohr radius is, which is A0, which takes a certain value. So when we put in Rn as this value in here, we get N is equals to 435. So basically, find the quantum number of the Bohr orbit in a hydrogen atom whose radius is this. So in this orbit, in this radius of if the radius of the electron orbit is 0.01 millimeters, then that would be the 435th quantum number. ठीक है? What is the energy of a hydrogen atom in this state? We know that energy En is equals to E1 divided by N squared. So minus 13.6 divided by 435 whole squared. So we will get this value for the energy of the hydrogen atom in this state, or the energy of the electron in this state. ठीक है? So Rydberg atoms are extremely fragile and easily ionized, which is why they are found in nature only in the near vacuum space. ठीक है? So yeah. Any questions so far? No questions? Okay, then we'll talk about the hydrogen spectrum, and this is very easy. Again, we have, I'll just go through this really quickly. Initial energy, if the quantum number of the initial higher energy state is Ni, and the quantum number of the final lower energy state is Nf, we are asserting that initial energy minus final energy is the energy of the photon. Obviously, if the photon is, if there is initial energy minus the final energy will be the photon energy, ठीक है? will the change in the energy of the orbits causes either the release of a photon or the absorption of a photon. And soon we're going to talk about lasers also. After we finish with this topic, we will talk about the laser also. Okay, so we have the initial energy minus the final energy is equals to hf or h nu, which is the nu is the frequency here. This is the frequency of the emitted photon. So from 4.15 we have, where's 4.15? Wait a minute, yeah, we're on this slide. And 4.15, well, I think we all know that. So we have this equation. I already just explained this equation, TK. And if you want to change reverse the sign, take this multiply by minus sign. You would just take minus common, and then this will be minus E1 and 1 over NF squared minus 1 over NI squared. We recall, so E1 is a negative quantity because it's minus 13.6 electron volts. So that means that so minus E1 is a positive quantity. Okay? So obviously because E1 is negative, so minus of E1 is going to be a positive quantity. So the frequency of the photon released in the transition is therefore frequency is, we know that this equation over here is equals to HF. So HF is equals to minus E1 times its factor. So if you want to figure out what the frequency of the photon released in the transition is from an initial state to a final state, then you will write here frequency is equals to this term divided by H. Tk is equals to E1 minus E1. Then you will substitute this for this part, for this. You will get minus E1 over H times this thing. And we know that lambda, the de Broglie wavelength, the wavelength that is released, this is not the de Broglie wavelength. This is the wavelength of the photon, is equals to C over frequency. So 1 over lambda will be equals to frequency over speed of light. So this frequency over here, if you divide by speed of light here and here, you will get V nu over C, which is 1 over lambda. So 1 over lambda is equals to this equation. So this is the hydrogen. This is the equation for the hydrogen spectrum. ठीक है, जो हमारे पास lambdas जो release होते हैं, ठीक है, of the lambda wavelength of the photons that are released, that will be given by this equation, ठीक है, where this is the final state of the electron orbit, the final state, and this is the final quantum number, and this is the initial quantum number. And we have done this in astronomy and astrophysics before as well. So I'll just quickly go through this. So if NF is equals to 1, then we will put here 1. And this will be the Lyman series, and n can be 2, 3, 4, etc. This n can be 2, 3, 4 higher numbers. Then we have the Balmer series. Which is when n is equals, nf is 2, and then we have the other n's can be 3, 4, 5. Nf is 3 Paschen series here, and this n can be 4, 5, 6, etc. Bracket series, and F is 4 here. Okay, we are studying 2 new series here. Okay, we didn't study this before. So we have an F is 4, and then these can be 5. The rest, the N can be 5, 6, 7, etc. Then we have an F is 5, and this can be 6, 7, 8. This N can be 5, 6, 7, 8. Okay, so yeah. So our final step is to compare the value of the constant term in the above equations with the Rydberg constant. Okay, so Rydberg constant is given by this value, okay? These constants. So when you put the values, numbers in, you will get 1.097 10 raised to the power 7 meters, meter inverse, meter power minus 1. So that was all. Wait, we have one example. We still have one example to go in this topic. So find the longest wavelength present in the Balmer series of hydrogen corresponding to the H alpha line. So in the Balmer series number, the final state is n is equals to 2. So this number is going to be 2 here. Find the longest wavelength. Now, if you try to understand, look at this formula over here. This will be longest when this whole thing is going to be smallest, right? Because it's 1 over lambda. So lambda will be longest. If we want the longest wavelength, then we want this number to be the smallest. When this number is the smallest, that means that this number should be this number should be smallest means that this number should be what? Largest, right? इस number को हमें जितना small चाहिए, मतलब कि difference should be small. This number will be 1/2 square. ये तो fixed है. If we want this to be the smallest, then this number should be the largest. This number will be the largest when it'll be divided by 1/3 square, because if it's divided by 1/4 square, that's 1/16. This will be larger. We want this to be the smallest. Are you all getting me? What I'm saying here? So 1/2 square minus, we will put here 3, because when this is going to be 3, then this is going to be the smallest difference. And when this is the smallest difference, we will get the longest wavelength, because we want this fraction 1/λ to be the smallest. So then we will get this number here. When we put 1/2 square minus 1/3 square, we will get this in terms of capital R, where capital R here is a Rydberg constant. So lambda is equals to 1 over, when you rearrange, because we said 1 over lambda is equals to this now. So lambda is equals to 1 over 0.19339 R. So we get this equation. We get this formula. We put in the value of Rydberg constant, then we will get this wavelength. So this is the longest wavelength present in the Balmer series of hydrogen. Okay? Now, are there any questions related to what we have done so far? We will start lasers now, if there are no other questions. What do you all know about laser? The term laser stands for light amplification by stimulated emission of radiation. Okay? The term laser stands for light amplification by stimulated emission of radiation. And we're going to study what exactly lasers are and what their properties are. Okay? So what do we know about laser? Laser is a device that produces a light beam with some remarkable properties. Okay? So laser is basically a device that will produce a light beam that has very certain properties. Okay? One property is the light is very nearly monochromatic. What do we mean by monochromatic light? Anyone can tell me?
Ma'am, unidirectional or
no, but they have all the same frequency. They have the same frequency, because monochromatic means the same color, right? And color is dependent on the frequency or the wavelength. Yes. Okay, Tika. So we mean by monochromatic is that they have the same frequency. If you could look at this diagram, Tika, ordinary light might have different frequencies. They will have different phases and etc. But monochromatic incoherent light is given by this thing. Lasers now, they are very nearly monochromatic, means that if you have a laser beam coming from a certain laser device, they will all be of the same frequency. The light, they will be all of the very nearly monochromatic, very nearly of the same frequency. The light is coherent with the waves, all exactly in phase with one another. So if you look at this figure over here, this is ordinary light. Ordinary light can be out of phase. It can be not necessarily the same frequencies. But if you look at this diagram, this one is the monochromatic. They all have the same frequency, but they're not necessarily in phase, as you can see over here. The one crest does not correspond to the other crest and the trough, etc. So, but then we're talking about lasers which are also coherent. Means that this is monochromatic light which is also coherent. Means that they are in phase with each other and they're all the same frequency. So this is the best diagram for the laser. Okay? And then there's four properties of a laser. A laser beam diverges hardly at all. Okay? So such a beam can send from the Earth to a mirror reflect. This is not very important. This is just an example over here, but it diverges hardly at all. And what do we mean by divergence? That means that if you have a beam, a device that produces a laser beam, it's going to come out in a narrow beam. Okay? It's not going to diverge so much like this, or like this, or like this, etc. Okay? It comes out mostly in a beam. And then the beam is extremely intense, more intense by far than light from any other source. The beam is very intense. That means that if you want to achieve the energy density equal to some laser beam, to achieve an energy density equal to that of some laser beam, a hot object would have to have a temperature of 10 power 30 kelvins. that is a very high temperature, okay? So the laser beam is very intense. That means it has very high energy density. Okay? Energy density means the power per unit area. And yeah, energy per unit area or per unit volume. It depends on what you're considering to be the surface density or the volume density, okay? So basically, laser beams have a very high intensity. So if you want to produce some object, if you want an object to have intensity similar to that of a laser beam, that object should have a temperature of around 10 power 30 kelvins. So that is a lot. Yeah, anyway, so these are some properties of the laser beams. So now we will talk about stimulated emission, spontaneous emission, and absorption. And stimulated absorption, stimulated emission, and spontaneous emission. So do you all know the differences between them? So let's talk about the differences between them now. Now, 3 kinds of transitions involving electromagnetic radiation are possible between 2 energy levels. Okay? Between 2 energy levels, if you have 2 energy levels, here we have E1, and here we have E0. Now, what are the possible transitions that can happen? Well, one we know is this transition, one we know is this transition, okay? Now, this one going from E1 to E0, it would lose energy, right? Because E1 has a higher energy. So what would that be? Now, if the atom is initially in the lower state, it can be raised to E1 by absorbing a photon of energy E1 minus E0, which is equals to HF. This process is called stimulated absorption. So if I want to draw a diagram that if I want to show you a diagram, then if we start off from E1 and the electron jumps to start off from E0, electron jumps to E1, what are we going to get over here? ये किस तरह से हमें मिल सकता है? Obviously, it's going to absorb some energy. From a photon is incoming. The electron will absorb the energy. It will jump to a higher state. This is called stimulated absorption. Stimulated means that a photon has stimulated the absorption to take place. Okay? The photon has been there to stimulate this absorption and this jump from the lower state to the higher state. That's what we call a stimulated absorption. Okay? So basically, if we have an atom initially in the lower state, E0, it can be raised to the higher state by absorbing a photon. This is called stimulated absorption. The next one is if the atom is initially in the upper state, and then it will jump to the ground state by the release of a photon. And if this happens without any stimulation of any photon, then it's called spontaneous emission, because this event has happened spontaneously. What do we mean by spontaneous? Randomly, right? It means spontaneously means like randomly, without anything else like occurring. Yes? So that is known as spontaneous emission. Okay? If an atom is initially in the upper state, E1, it can drop to the lower state by emitting a photon. This is known as spontaneous emission. Now the third type is known as stimulated emission. And what else can happen in this situation? If another photon has, now if the electron is initially in a higher state, and if a photon is incoming, it will stimulate the electron to jump from the higher to the lower with a release of 2 photons. The initial one is also released, and the energy that the energy released due to the jump of the electron from the higher to the lower will also be released as a photon. So this is called stimulated emission. Einstein in 1917 was the first to point out the third possibility, which is stimulated emission, in which an incident photon of energy, HF, causes a transition from E1 to E0. Okay? So this stimulated emission, the radiated light waves are exactly in phase with the incident ones. So the result is an enhanced beam of coherent light. Show the stimulated emission has the same probability as stimulated absorption. Photon. So do you understand what the difference between these three types of emission and absorption. So stimulated emission is basically, stimulated absorption is when the electron is in the lower state and it absorbs a incoming photon. There's a photon incoming and it will be absorbed. The electron will absorb the energy from the incoming photon. It will jump to the higher state. So this is stimulated absorption. Spontaneous emission is when electron would jump from the higher state to the lower state spontaneously or randomly without. It will also release a photon, but no, there was no photon initially present. Initially, that was stimulating it. The third case is when we have a photon which is stimulating the electron to jump from the higher to the lower state. This photon will be released as well as another photon will be released. ठीक है? So what they're saying here is that Einstein showed that stimulated emission has the same probability as stimulated absorption. That is, the photon of energy HF incident on an atom of the upper state E1. A photon of energy incident on an atom in the upper state has the same likelihood of causing the emission of another photon as its likelihood of being absorbed. That means that if you have this situation or this situation, both have the same probability of, the probability of absorption and emission are the same. Stimulated emission has the same probability as stimulated absorption. Okay? So both have the same probability of occurring. That is, if a photon of energy HF is incident on an atom in the upper state, now we have this one where there is in the upper state, this one is in the upper state, okay? Electron in the upper state. The photon of energy HF incident on an atom in the upper state has the same likelihood of causing the emission of another photon as it has of being absorbed if it is incident on an atom of the lower state. So this event has the same probability of occurring as this event. ठीक है? Any questions so far? So this is absorption from the lower to the higher state. It will absorb the energy from the photon. This is spontaneous emission. That is, from the higher state, it will jump to the lower state and it will release a photon. And then we have stimulated absorption, where we have the photon is incoming, ठीक? And then it will stimulate an electron of the higher level to jump to the state of to orbit of a lower level. And with the release of two photons, this initial one and the one that is released due to this jump. Okay, so any questions? I think we have completed this chapter of atomic structure, and we took half of this lecture for this chapter, and I think. So are there any questions so far related to lasers or any of this hydrogen spectrum, anything that we have done so far? We have this next chapter. Okay, so we have this next chapter.
No, ma'am.
Okay, nuclear structure. So now we will be doing this chapter, which is nuclear structure. Okay? This is lecture. This is lecture number 7. I mean, I just called it because this one I called it lecture 6. So this is book chapter 11. This is chapter 11 from the book, and it's called nuclear structure. So I think we can go ahead with this chapter. Yeah. So nuclear composition. Like I gave you one assignment to do that was due by Wednesday, ठीक है? So इसमें से कुछ चीजें हम इसमें भी करेंगे, like isotopes करेंगे. इसमें हम nuclear structure को देखेंगे, ठीक है? Nuclear composition को देखेंगे. कि what are the different properties of the nuclear atom, and we're going to do we're going to talk about isotopes and nuclear radii, and we will do some examples related to those as well. And we will talk about binding energy. And then we were binding energy per nucleon and those kinds of things. Some things are similar to what we have done in astronomy and astrophysics, but still we'll be doing some newer things here. Okay? So nuclear composition. And the reason why I'm trying to go a bit faster is because we have only 1 month left and we have 3 chapters still. So I just want to hurry up a bit. And we also need to have a few more quizzes still. Okay? So we only had 3 quizzes so far, so we need more quizzes as well. So nuclear composition, atomic nuclei of the same element have the same number of protons. So what do you know about nuclear composition? Now, this is very easy. This chapter is quite easy, actually. It's not going to be very difficult. But what do we know about nuclear composition? We have the central nucleus, which contains protons and nucleons, right? Which consists of protons and neutrons. And then we have the orbits around it, which is consisting of the electrons in the orbit. So this is a nuclear structure. So atomic nuclei of the same element have the same numbers of protons, but can have different number of neutrons. So if you have an atom of the same element, for example, हाइड्रोजन का एक एलिमेंट है, ठीक है, उसके अगर what you by if you have the same number of protons, it will always be the same element, but you can have different number of neutrons, and those will be the isotopes, right? So the electron structure of the atom was understood before the composition of its nucleus was known. The reason is that the forces that hold the nucleus together are vastly stronger than electric forces. So so what we're talking about over here is that an ordinary hydrogen atom consists of a single proton whose charge is positive E, whose mass is 1836 times that of the electron, about, ठीक है? All other elements have nuclei that contain nucleons as well as protons, neutrons as well as protons. So what do we mean by the term nucleons? Nucleons refers to protons as well as neutrons, ठीक है? Neutrons and protons are jointly called nucleons. So what we have in the structure of a nucleus is that we have the central nucleus, which contains nucleons. The reason why we call it nucleons is because they're all in the nucleus. That's what we call them, nucleons, and they consist of protons and neutrons. Then we have around them we have the electrons. So the neutron is uncharged. We know that a neutron is uncharged, but it has the mass slightly greater than that of a proton, but still comparable to that of a proton. The mass of the electron is 1836 times less than that of a proton, ठीक है? So now we have the atomic number of an element is the number of protons in each of its atomic nuclei, ठीक है? So we have atomic, what do we mean by atomic number? And how we can relate it to the symbols of an atom. The conventional symbol for nuclear species or nuclides, it goes by A, Z, and X, ठीक है? X is the chemical symbol of the element, Z is the atomic number or number of protons in the nucleus, A is the mass number of the nuclide or the number of nucleons in the nucleus. So Z here is the number of protons, and A is the total number of protons plus neutrons. So obviously A minus Z would give you the number of neutrons. So the atomic number is the number of protons in the nucleus, ठीक है? Which is the same as the number of electrons in a neutral atom of the element. Obviously, if the atom is neutral, then it will contain the same number of protons and electrons. Thus, the atomic number of hydrogen is 1, of helium 2, lithium 3, etc. ठीक है? All nuclei of a given element do not have necessarily equal number of neutrons. For example, in hydrogen, you can have you heard of deuterium before? Deuterium and tritium, ठीक है? They are isotopes of hydrogen, ठीक है? They're isotopes of hydrogen, deuterium, for example. And here they've shown you hydrogen, deuterium, tritium, ठीक है? Hydrogen has one proton and one electron, but deuterium has one extra neutron and tritium has 2 extra neutrons. So that these are isotopes of the same element, which is hydrogen. So isotopes can contain different number of neutrons, but they will always have the same number of protons because we're considering the same element. And one particular element will always have the same number of protons, basically. ठीक है? And if you consider like यहाँ पे एक electron है, अगर एक electron इसमें add किया जाए, that will be an ionized version of the hydrogen atom, ठीक है? That'll be an ionized hydrogen atom. If you remove this electron, that will also be ionized hydrogen atom. ठीक है? So we talked about ionization energy in the previous PowerPoint. But anyway, here we're talking about isotopes, ठीक है? So heavy water is water in which deuterium atoms instead of ordinary hydrogen atoms are combined with oxygen atoms. So when you have instead in water, you know that we have H2O. So we have hydrogen atoms in there, 2 hydrogen atoms and 1 oxygen atom, ठीक है? So when you have deuterium instead of hydrogen in the water molecule, that will be called heavy water. And that is just a name for one of the different types. For water that contains isotope of hydrogen, deuterium. ठीक है, so now we talked about the conventional symbols for nuclides, which is given by this is the symbol of an element, and Z here is atomic number of protons in the nucleus. A is the mass number of the nuclei, the number of nucleons in the nucleus. A is the number of neutrons plus protons, and Z is the number of protons. And Z will be equal to the number of electrons also if it's an unionized, if it's a neutral atom, basically. Okay? So what we're saying here is that ordinary hydrogen is 1 hydrogen, deuterium is 2 1 hydrogen. Isotopes of chlorine now. Chlorine has 17 protons, and nuclei can contain 18 or 20 neutrons. So for example, in this situation, this would have 18 neutrons, 35 minus 17, and 37 minus 17 is 20. So that would be the 20 neutrons here. Every element has a characteristic atomic number. Atomic number is not going to change for different isotopes of the same element. Atomic number will always remain the same for a particular element. ठीक है? You can read this as chlorine 35 or this as chlorine 37. So anyway, so let's talk about atomic masses now. Atomic masses refer to the masses of neutral atoms, not of bare nuclei. Thus, an atomic mass will always include the masses of its Z electrons. So atomic mass basically is the mass of the neutral atom, not just of the nucleus, ठीक है? Atomic mass, जो हमने अभी कहा था कि ये जो symbols हमने represent किए थे यहाँ पे, this A here is the number of nucleons, number of neutrons plus number of protons. But over here, what we're doing is now we're talking about atomic masses, which is something slightly different, is that atomic mass will be the mass of the neutral atom as a whole. So it will always include the mass of the Z electrons that are there as well. Atomic masses are expressed in mass units, which is U, ठीक है? And what is the definition of a mass unit? Is 1 unit is equals to 1.1 atomic mass unit is defined as 1.66 times 10 raised to the power minus 27 kilograms, which is defined as a mass of a 12.6 carbon atom. The most abundant isotope of carbon is exactly 12 U atomic mass unit. So basically, if you by experiment, if you determine what the mass of this carbon atom is, ठीक है? That's exactly 12 U, so that gives us the value of one atomic mass unit, which is 1.66 in 10 to the power minus 27 kilograms. ये held हो गया था थोड़ा सा. Okay, anyway, so we're saying over here, equivalent of a mass unit is 9 mega electron volts. We know that energy can be measured in terms of electron volts or joules, ठीक है? So the energy equivalent of a mass unit, we know that E is equals to mc square, right? So that means that energy and mass can be interchanged with one another. In that situation, the energy equivalent of one mass unit will be equal to 931.49 mega electron volts, ठीक है? So this value I would give you, if I give you some calculations to do, then I would give you this value, that this is the energy equivalent of a mass unit. So table 11.11, which is this table over here, gives the masses of the proton, neutron, and electron, and 1 hydrogen in various units, including mega electron volts, divided by C squared. So now if you look at this table over here, now this is ये जो कटा हुआ है ना, ये 7 है, 1.6726 in 10 to the power minus 27, 1.007276. ये थोड़ा सा कटा हुआ है, लेकिन बुक में आपको क्लियर नजर आएगा, ठीक है? So anyway, the proton's mass is this, the neutron's mass is this, electron, a hydrogen atom is given by this one, ठीक है? तो ये जो हमारे पास hydrogen one hydrogen atom का है, this is the mass of a proton plus electron. This one is proton plus electron. ठीक है, इसलिए हमने इसमें ऐड किया हुआ है इसको. इस mass को इसमें add किया है. So in terms of mass units, one proton is 1.007276 mass units. Neutron is this much, almost one atomic unit, but not quite. This is also almost one atomic unit, but not entirely there. And then electron is this much of a mass unit, and one hydrogen is this much of a mass unit, atomic mass unit. And then we know that why is this mass written in terms of mega electron volts per c squared? Because E is equals to mc squared. That means m is equals to E divided by c squared. So mass can also be written as a unit of energy divided by c squared, right? Makes sense? Because we know that E is equals to mc squared, so E divided by c squared is equals to mass, right? So mass can be written as units of energy divided by c squared. So that's if you want to do the conversion of the protons, this atomic mass unit, these are the values for the energies, for the masses of these. This is a mass in different units, okay? This table gives masses in various units. This is in kilograms, this is in U atomic mass unit, and this is mega electron volts per c squared. So what is the advantage of this method? Advantage of using this unit of energy is that the energy equivalent of a mass of, say, 10 mega electron volts per c square is simply E is equals to mc square. So if you have a mass, say 10 mega electron volts per c square, mass in terms of mega electron volts per c square, then you can easily know that the energy equivalent of that mass will be 10 mega electron volts. Because it's mc square, so you just multiply this by c square, and the c square will cancel, you will get 10 mega electron volts. Make sense? So this advantage of this method, this knowing the masses in mega electron volts per c square is good for us because we can be able to determine easily the energy equivalent of that mass. Okay? So isotopes of hydrogen and chlorine, table 11.2 over here. Table 11.2 over here gives the composition of the isotopes of hydrogen and chlorine. Okay? So here we have hydrogen and chlorine, and you don't need to memorize this table, okay? Because there are lots of numbers here, but atomic number is 1 here, 17 here, average atomic mass is given here and here. Protons in the nucleus, 1 uska hota hai, 1. For these are the three types, the three isotopes of hydrogen, and these are the two isotopes of chlorine, okay? Number of protons will always remain the same for one particular element. Neutrons in nucleus, 0 for the hydrogen, 1 for the deuterium, and 2 for the tritium. And 18 for chlorine 35, and 20 for chlorine 37. These are the two isotopes of chlorine. These are the number of neutrons they would have. So the mass number will be 1 here, because mass number will be 1 here, because this is the mass number is given by this number plus this number. Here's 2, here's 3, and here's 35 and 37. Atomic mass units, you would multiply this mass number. Atomic mass unit किस तरह से यहाँ पे हमारे पास आए हैं ये numbers. Atomic mass total calculate किया है तो 1 proton plus electrons, 1 electron, 1 proton plus 1 neutron. These numbers, 1 proton plus 1 neutron plus 1 electron, 1 proton plus 2 neutrons plus 1 electron. So this is how we calculate the atomic mass. We will use these values over here because we are calculating in terms of atomic mass unit. Okay? And then similarly, we do the same thing for chlorine, relative abundance, which has been found by experiment or by observation. Okay? You have relative abundance of these different isotopes of hydrogen and chlorine. Okay? Hydrogen का 99.985 है, deuterium का 0.015 है, and tritium का very small है. Okay? And obviously, the sum of these three should be 100%. Similarly, these two also, like we have 75.53 for chlorine 35, and for 37 we have 24.47. And also the sum of these two should also be 100%. Okay? So I was on this slide. So what we're saying here is that 1/4 of this yields, we have about 3/4. As you can see from this table, 75% is approximately chlorine 35 and 25% is approximately chlorine 37. So if you want to calculate, it would be 3/4 times 35. The average, how would you calculate the average mass? How would you calculate the average mass of the chlorine? You would multiply it 75% times 35 and 1/4 or 25%, 25% times 37. And then you would get approximately an average mass of 35.46 U, atomic mass unit. Make sense? The chemical properties of an element are determined by the number of arrangement of the electrons in its atom. Okay? So chemical properties of any element, they're determined by the number and arrangement of the electrons. ठीक है? Electrons जिस तरह से arrange हुए हैं वो chemical properties होंगे उसके. Electrons किस तरह से arranged हैं atom में. ठीक है? And the number of the electrons as well. Since the isotopes of an element have almost identical electron structures, it is not surprising that two isotopes for chlorine have the same yellow color, have the same suffocating odor, the same efficiency as poisons and bleaching agents, same ability to combine. Because, okay, so basically what we're saying that chemical properties of an atom are dependent on the number and arrangement of the electrons. And because isotopes of the same element have the same number of electrons, they would have the same chemical properties like color or odor or what their efficiency as poisons or bleaching agents and ability to combine with metals, etc. But physical properties, boiling points and freezing points depend on the atomic mass, because boiling and freezing points are some part of their physical properties which depend on the atomic mass. So they're slightly different for the two isotopes, as are the densities, okay? Because these physical properties, chemical properties will depend on the number and arrangement of the electrons, but physical properties will depend on the atomic mass, okay? And so the boiling point, freezing point, they will depend on the atomic mass. And because we know that two isotopes have slightly different atomic mass, so they will have slightly different boiling and freezing points, as well as their densities will also be different because they have different atomic masses. So other physical properties of isotopes vary more dramatically with mass number. Tritium is radioactive, for instance, whereas ordinary hydrogen and deuterium are not. So we can have other physical properties of isotopes as well. They can be different because, like, for example, like hydrogen and deuterium are not radioactive, but tritium is. So these are some things about isotopes. And some nuclear properties, I think we will go, it's already 3:51, so I think we will start this topic. We will talk about nuclear radii and nuclear properties. I think we will do this in some examples in the next lecture. And are there any questions so far? I think we'll be able to finish this chapter hopefully in the next lecture.
No, ma'am. No questions.
No questions.
No questions? Okay, so I think this is not a very difficult topic, Tika. So, yeah, so you have, so the assignment is just 15 MCQs. They're very easy, Tika. It will be due by this Wednesday. And can we have a quiz next week on this chapter? When we'll be able to finish this chapter by Wednesday for sure. So then next week, sometimes we can have a quiz on this chapter, right? Either Monday, Tuesday, or Wednesday, any day of the week is fine. What do you suggest, all of you? Because we only have 3 quizzes, and ideally we should have minimum तो 4 quizzes होने चाहिए, ठीक है? Minimum 4 quizzes होने चाहिए, or at least if we have 5 quizzes, I will include the best 4. So that's also an advantage.
Excuse me, ma'am.
Yes.
Monday.
मैम इस वेंसडे को प्लीज ना रखें, हमारी असाइनमेंट ड्यू है इस वेंसडे को.
इस वीक में नहीं रखूंगी क्विज, नेक्स्ट वीक की बात कर रही हूँ.
मैम नेक्स्ट वीक की बात कर रही हूँ मैं भी. नेक्स्ट वीक तक ही हमारी एक असाइनमेंट ड्यू है, 9th of December, Wednesday.
Okay, let's see, just 1 second. So next week you're saying that 9th of December को assignment due है? वो तो बहुत दूर है. We can keep a quiz either 30th November or 1st December or 2nd December. One of these 3 days.
हम 32
हमारी
बस।
ATM की भी असाइनमेंट है मेरे ख्याल से
6 दिसंबर को
इसी
भी
वीक।
आएगी।
6
फाइनल
दिसंबर
इसके बाद
ओके मैम, इस वीक में रख लें मैम, ठीक है।
इस वीक में, नेक्स्ट वीक में?
यस मैम, नेक्स्ट वीक में,
ओके,
लेकिन उससे नेक्स्ट में नहीं।
30th, 1st और 2nd, इन तीनों में से कोई भी डे वी कैन कीप द क्विज।
या ओके,
ठीक है, चलें 1 दिसंबर कर लेते हैं फिर, ट्यूसडे।
मैम आप 30
ठीक है,
कर लें, 30 कर लें।
ओके ठीक है, 30th नवंबर कर लेते हैं फिर, ठीक है, 30th नवंबर कर लेते हैं। नेक्स्ट मंडे we'll have a quiz on this chapter because this is a, बल्कि ये जो हमने ये भी किया था ना, okay, I will see to the 30th November को इस chapter, this is a very easy chapter, but इस chapter के ऊपर रख लेते हैं quiz, and जो हमारे पास ये chapter था रदरफोर्ड स्कैटरिंग के बाद, डेरिवेशन के बाद जो हमने किया था वो भी इंक्लूड कर लेते हैं ना, चैप्टर स्लाइड्स 25 से लेके 56। Is that okay?
मैम बस उसी अगले चैप्टर का ही रख लें, क्विज पिछले का फिर अलग से रख लें फिर सारे चैप्टर का।
ओके, तो फिर मंडे को हम बल्कि इस चैप्टर का रख लेते हैं, पहले एटॉमिक स्ट्रक्चर का क्विज खत्म कर लेते हैं ना, स्लाइड्स नंबर 25 से लेके 56 ऑफ एटॉमिक स्ट्रक्चर का क्विज रख लेते हैं, फिर उसके बाद फिर इस चैप्टर का क्विज ले लेंगे, ठीक है?
ओके
I will write that in the WhatsApp as well, the group as well, so that we all sure about it.
मैम ये स्लाइड्स भी शेयर कर दीजिएगा।
Yeah, I will share. I think I shared these slides already in MS Team. Slide number lecture 7. I think मैंने already share कर दिया है इस पे files पे. Class materials, yes, lecture 7 nuclear structure ये हो गया है share already. ठीक है?
Yes, ma'am, thank you.
Okay, so that's all for today, and then we will continue the same chapter tomorrow and day after tomorrow, and we'll hopefully finish the chapter soon. And so we have to finish our syllabus quickly because January के first week में exams होंगे, ठीक है? Final exams. I don't know if you all know about it yet or not.
मैम जनवरी के फर्स्ट वीक में तो नहीं होना शायद।
I'm not 100% sure right now कि कब कौन से डे में शुरू होंगे, लेकिन जनवरी में ही होंगे एग्जाम्स, फाइनल एग्जाम्स।
मैम जिस सेमेस्टर प्लान शेयर किया था वो उन्होंने कि उसमें था कि जनवरी के 3rd वीक में थे।
अच्छा, I'm not sure yet. I think they will send an email soon. ठीक है?
Okay.
Okay, so let me download the attendance list as well. Okay, so I think that's all for today, ठीक है? And then we'll continue tomorrow. ठीक है? Okay. If there are no more questions, then I will end the meeting now. And so, Allah Hafiz.
खुदा हाफिज़।
Allah Hafiz, ma'am.
Hafiz.